0.0333?
No. I mean, what's the error in this equation? This, right? So if I make E equal this and I solve for n, I end up here. Is that all right? We already did that basically once. This is a little bit worse, but it's the same idea. Same way we calculated n before, but now if I want to, how large a sample do I have to take to be within so much percent? I've got to use that. And what's going to drive me a little bit crazy is that we will almost never put the percentage number into an equation. The only time we'll do that is if we create an equation and our inputs are percentages. You ain't never done that, so you ain't never going to do it till we do it. So what should I put in for E? What did I just say? 0.02. 2%. All right. So on one level, every number is made up. We had to come to some agreement about how to represent numbers. So our number 2, it looks very different in ancient Chinese. It looks very different in Babylonian mind. But, so there's an idea of a number. The percentage is something extra that humans made up. We just said, okay, everything out of 100, let's just put a percent symbol. And because it's easier to grasp. 0.037, 3.7%, much easier for us to grasp. We can imagine that slice of the whole pie. You guys semi with me? So I'm going to put that into an equation. It's got to be the actual number that represents. That represents 0.02. Please, dear God, it's not 0.2. Right? That's 20%. All right. So try to figure it out. You know everything you need for that. Still the same problem. All right, we know P hat, we know Q hat. That's what that looks like. We just throw all that shit in there. I don't know, what do you guys think?
1804.62 rounded up to 1805.
Cool, man. Let's see if I can do this myself. You can do it, Jeff, can you? Yay! So 1804 point stuff, so I rounded up to 1805. And again, you can do the same thing. I need 1805 total. I've already talked to 652, so I really just need 1100 something to get my error to be that small. Okay, maybe.
Was 1805 a good year?
Huh?
I said, was 1805 a good year?
A good point. I don't know. I think it was kind of rough. All right. You guys all right? I mean, there's a lot of concept that goes into creating the equations. And the more you understand those, the more sense the equations will make. But if you don't understand how that works, shit, I would never teach it like this, but you got the equations. It's just plug and chug. You just have to know when to use which equation, right? Okay, so let's do one more idea for today, and then I'm going to let me out early, and you guys can leave too. It's pretty much always the truth of that, how that works. So, all right. Leave the periodic table. Is it going to come down? You're going to get attacked by the elements. All right, guys. So, now I can't get. We're about to get into. Let me ask you this very strange question. Does anybody drink Guinness? Anybody know what Guinness is? There it is. It's a really dark beer, right? Anybody happen to drink Guinness? Anybody? No? Okay. So maybe you won't be interested in this. The next idea we're going to discuss was created by somebody who worked at the Guinness Brewery. And that's a word that makes you sound drunk. Where were you? It was at the brewery. All right. And that has nothing to do with the actual thing, but it's just nice to kind of know the history. It's kind of interesting. He wanted to publish his findings, but his findings were related to studies he did on things there at the brewery. And anything that he came up with was supposed to be legally their property. That was in the contract. So he actually published it under a pseudonym, an alias. Called himself Student. He's a very creative guy. William Gossett was his real name. We know now, right? He's in his grave. He's going to be fine. Just as fine as he's now. Dead. So, what he did was this. He said, okay, Section 8.1, somehow he knew ahead of time how this book was going to look. He said, that's just fine, but what's wrong with that section? So in that section we did this. We did this equation. This part is remarkably honest, because normally I walk into a situation, I don't know the actual mean. But going hand in hand with that is I also should not know in a lot of situations, not always, so it's not invalid. But what happens most often is we don't know shit, so we don't know that. So let me ask you this. If there is a piece of what I'm working with that I'm not sure about, so if I don't know sigma, what's the next best thing I can use? What does sigma represent? Not good enough. What's sigma represent? The what? Standard deviation of a population. So if I don't know that, what's the next best thing? S, standard deviation of the sample I take, right? Because where am I going to get x bar from? Sample. So can't I also figure out what S is? Especially if I don't know what sigma is, I'm going to have to. Okay. And let me say this right now. If I do know sigma and I take a sample, can't I still calculate S? Yes? If I take a sample, can I calculate S? Yes. I can put in 1 bar stats and do that shit. Am I going to use S if I know sigma? Hell no. S is an estimate for sigma. So there are problems in the book. And there could be, I don't know, problems on the test or something, where you know both. If you know sigma and S, screw S. I'm going to use sigma. S is an estimate for sigma. So if I know that one, why the shit would I use S? I have no idea if what I just said makes sense to you, but there are problems like that in the book. I'm not going to use the estimate for something when I know the something. I'm going to use that thing, right? If I knew the population mean, I wouldn't do this thing at all, because that's what this thing tries to do. Okay. But if I don't know sigma, I must use S. So therefore, I can't use that. Well, what should I do if there is a part of what I'm working with that I'm not sure about? Namely, the S. Do I know if it's the same as sigma? In fact, I would probably put money on it being different, right? If you take a sample and find its standard deviation, I'll bet you all the money I've got that it's not the same as sigma, right? Don't go out and create one that makes it happen. I'm talking about just a random sample you take. Oh, look at this one. All your money, please. Get out. You guys semi with me a little bit? So what should happen if I am using something I'm not as certain about? What should happen to my interval? Should it stay the same size? Should it get bigger? Or should it get smaller? It's got to get bigger. In fact, the way I love to look at it is, this kind of works. If there's something in my equation I don't know what, I'm not certain about, like S, I got to cover my ass more. So my interval's got to get bigger to be equally confident. So maybe if I knew sigma, the confidence interval could be something like 5 to 7. But if I don't know sigma, maybe it's now 4 to 8. Because if I'm not sure about something, here, coming back to my fish analogy. This is going to get a little weird, and apparently I don't care because I'm going to do it anyway. There's a certain fish I want to catch, right? but I'm not sure how wide it swims. Am I going to have to throw out a bigger net because of that or a smaller net because of that? Throw out a freaking bigger net. Shit. So if I don't know the spread as well as I should, I'm going to throw out a bigger net. And the net is the confidence interval itself. So what this means is, instead of using a z-score, I'm going to use something that is just a little bigger sometimes than the actual. It's always going to be bigger than the z-score. I've got to make my confidence interval bigger, which means my error is going to have to get bigger. So these things are called t-scores. Just because. Right? Totally. I don't know why. To be honest, I keep forgetting that. I think at one point in my life I knew why we called it t-scores, and now I don't remember. What the hell? Why do we call them z-scores? I don't remember that either. Shit. So, the basic idea then is, for a 95% confidence interval, this would be 1.96. We've done that a few times. You guys with me? But for a 95% confidence interval, this could be like 2.04 or 2.79 or something. It's going to be bigger than 1.96. When would I be more certain about this guy? If what's true about my sample? It's got to be big. The bigger my sample is, the less I've got to cover my ass for not knowing this, but it's because the more certain I become about this. So this covering of my ass depends on how big my sample is. If I got a really small sample, oh shit, I need this thing to be big. Cover my ass a lot because I really don't know about it. Take 3 people. Oh shit, how close is that going to be to that? Who the hell knows? Take 800 people. Okay, I don't need as much ass covering, thank you, because now I feel a little bit better. I don't know, you guys. Let me give you this. Based right off of what I just said. Here's the chart. Yay. There you go. Yay. Was it last? I think it was in the class you were in last year. There was a couple people that were keeping track of how many times I said shit. Instead of taking notes. It's interesting, but you might be passing if you were doing notes instead of that. All right, so let's see how to read this thing. There's one very important idea, real quick. Let's just get this out the way. I always forget about this until we get to this point. Okay, a little side note. Just stay with me. This kind of sucks. I wish I would have done this earlier, but actually, let me do this first. Screw it. This is basically the sample size. Just go with me. We're going to talk in a minute what the hell this means. Degrees of freedom. You can't take away my freedom. So look at how these are the t-scores. These are basically the sample sizes. What's happening to the t-scores as my sample size gets bigger? And in fact, if my sample size is large, then what do these look like down here? Especially look at this one and this one. What are these at the bottom? Z-scores. Remember earlier we got 2.33 for 98%? Okay. So in the event that my sample is large enough, and I love how they leave it vague because it depends on the situation. What's large enough in one situation might not be in another. But if it is large enough, I could just go ahead and use z-scores. I don't need any ass covering, right? But the smaller my sample gets, the bigger the associated score gets to cover my ass. Because I'm going to be less and less certain about the S I'm using. All right, so now let's address what the hell degrees of freedom are. This is a really neat idea, and it actually goes back to chapter 2, in a sense. Let's do this. You ready? All right, I got 3 numbers. They average to be 10. Do you know anything about the individual numbers? Not a damn thing. That could be anything. But do you know anything at all about the collection of numbers? If they average to be 10, What's the only way three numbers can average to be 10 if they add up to be 30? How the hell does he know that? How do you find the average? None, yeah, it could. You could take 10, 10, 10. But how does something average to be 10? It's got to be the sum divided by 3. And what do you divide by 3 to get 10? 30. So I know they have to add to be 30. So how many numbers can I just make the hell up before I've got to be careful? And it's sort of like what I did with the probabilities too. I got to the end and then I stopped and it was, oh shit, I got to make it become 1 now. Same idea. So I can just make this up totally. 12, 3, and then I go, oh shit, now I got to make it do what? Add up to be 30. So what's the last number got to be? 15. So if you average 12, 3, and 15, yeah, it's crazy. No, all right. Are you guys semi with me? So degrees of freedom really is just, in the event you have n things, how much freedom do you have to just make shit up? Well, how many things was I able to just make up total? 2 of them, right? I made these 2 up. I can just make them whatever I want to. I can make the first one -8 and the second one 500, and then I can just figure out what that has to be to add to be 30, right? If I had 18 things, how many of them can I just make up? 17. It's just at the end I got to go, oh, wait, I got to make this work. Now, to be honest, there's a little more to this story, but this is enough for right now. So if I have n things, the degrees of freedom is always going to be n minus 1. This showed up earlier this semester for very much the same reason. Remember when I calculated the sample standard deviation? I didn't divide by n, I divided by... Yeah. That's neat. There's a whole big story in that thing that I really don't have the time to get into. But if you research, anyway, if you want to, degrees of freedom, standard deviation of a sample, it's neat. But it's enough for right now. So if my sample size was 37, what am I going to look up? 36. It's amazing. So that column is degrees of freedom. So what's the actual smallest sample this table works with, which kind of makes sense? 2. Because then I have degrees of freedom 1. Look how big the t-score could be in that case. If you took a sample of 2, you don't know shit. And so it's going to be like, normally you put about 2 for a z-score. You got to put a 63.657. You're going to just blow that sucker up. Maybe go take a bigger sample in that case, right? Okay, now, so that's one piece of reading this. The other piece is look at the top. What in the hell? Right? And you guys at home, you don't even know, right? All right. So the top, area in 1 tail, area in 2 tails. What? All right. So if I make a 95% confidence interval, how many tails does an interval create? And what the hell does that mean? What's the interval look like? This. How many tails did I just make? 2. Okay, 2 tails. If this is a 95% confidence interval, how much total area is in 2 tails? 95% in, 5% out. Is that cool? So which one of those columns would I look at? 0.05. If you cut it in half and say there's 2.5% in this one tail, do you see how you're still in the same freaking column? Right? Kind of covers you for that. Okay, maybe. So what confidence level is this column here? 90% confidence would be this one because there's 10% in 2 tails. You guys see how to read this? So basically, you could look at the 2 tails one all the time for area for confidence intervals. The next chapter we're going to do, like, we're going to test claims. So then it's going to be 1 or 2 tails. So like, for example, if I thought somebody, the average was actually greater than something, that's 1 tail because I just care about that side. So that's why they break it up the way they do. Okay, so let's try a couple situations out. Let's say that n is 37. I want a 98% confidence interval. And I know I don't know sigma. only know S. In fact, let me really, I'm going to say this multiple times. But why were t-scores invented? I use them when I don't know sigma, when I only know S. That is it. Now, what always has to be true before I could do anything? What do you think? I have to be working with a normal distribution. Is this normal enough? Yes, I didn't say it was, but n is bigger than 30. Okay. So what's my degrees of freedom? 36. What's my area in two tails? 0.02. Right, 90% in. So how much is in the tails? 2%. Can you guys, so say it out loud, look it up on the chart real quick. What t-score would you use? All right, what do you got?
2.434.
Yes, 2.434. You guys see that? I like it. And what we use, now watch. All right, what about this situation? Oh shit, you still don't see that, too bad. How about this situation? Let's say I got n equal to 84. And sigma is 7, and I want a 99% confidence interval. What score would I use? Ooh, why am I going to use a z-score? Two things.
Do you have sigma?
I know sigma, and is normal enough, because it's sample size. How can I use the t-score chart to look up the z-score I want?
Use the large values?
Yes! So if I go, what column am I going to look at? What's my area in two tails? 1%. If I stop, I get a t-score. I want a z-score, so I just don't stop. Weehaw! 2.576. That's what I'd use. And we already know some of these. Again, we've already done some of these. Remember the little baby chart I said existed earlier? This is like the baby chart on crack, right? You got a few more, or your favorite chart choice. The baby chart, I think, has this one, and this one. And then this one fills in a few more. Plus, now it can do all the t-scores. So, yay. So I will use the t-score chart to look up z-scores because they exist at the bottom. Now, please don't write notes on your charts. You should know that by now. Don't put any notes on your chart. Okay. No. Okay, so let me give you this. Damn it. Did I bring it? That would have been useful. But did I already give it to you? What's on the other side? Yes, I did. Other side of that one we just did earlier. There we go. Do the first problem on that. Actually, the first two problems. We're going to do the last one together. Do 1 and 2.